In this unit, we're going to move on to a completely different topic. We're going to learn to describe curves by parametric equations and a special kind of parametric equation called a polar curve. And we are also going to learn to extend all of our calculus ideas to these different curves. So first, here is the general problem. So suppose you have a little particle that moves along this line. Well, this curve, let's say, because it's not a line. So the problem is you can't describe this by a function because it fails the vertical line test. So here's the general problem. So first thing is you have some kind of particle that moves along this curve. And the problem is that you can't describe C by a function of x because this fails the vertical line test. It's not a function. So what you do instead is you use something called a parameterization. Parameterization. You say x is equal to some function of t, and y is equal to some other function of t. So you have this variable t that might stand for time, but it could just stand for something else or nothing at all. But you have this thing, then that t is called your parameter. And you plug that parameter into an equation that gives you the x-coordinate and an equation that gives you the y-coordinate. And these two equations, these are called parametric equations. And really, this applies to all sorts of things because this C really could be like the path of a road. If you looked at, say, roads on a map, most of them are not functions. They double back on themselves and stuff. So this little point could be describing the position of your car along that road at various times. All right, let's sketch a curve that is defined using parametric equations. And we're going to indicate with an arrow the direction in which the curve is traced as t increases. So I'm going to make a table of values. I have been told that t is between -2 and 3. So we'll have a t column, an x column, and a y column. So when you input t equals -2 into this x equation, x will equal 4 minus 2, or 2, and y will equal 2 times -2, or -4. So our first point is that 2, -4. Notice that the t-coordinate does not get plotted, it just determines where that point is that we plot. And let's just plug in every number, every whole number up until 3. -1, x will equal -1 squared is 1, 1 minus 2 is -1, and y will be 2 times -1, which is -2. So our next point is the point -1, -2. So from the origin, go back 1, down 2. And our curve starts by going from there to there. And since we started on the right and went towards the left, we're going to draw an arrow pointing in that direction. Okay, when t equals 0, x is -2 and y is 0. So we've gone to this point. When t is 1, x is 1 minus 2, or -1 again, and y is 2. When t is 2, x is 2 and y is 4. And finally, when t is 3, x is 7 and y is 6. Okay, and there we have, I mean, I put lots of arrows there, but you only need one. So indicate with an arrow which direction the curve is traced as t increases. Now, also notice here that this curve stops at those t values. And the reason is that, so my point is that we don't say you shouldn't draw an arrow indicating that this curve keeps going, because you do have this restricted domain. So be careful about that. If there's no restriction on the domain, you can indicate that the curve keeps going forever and ever and ever. But if there is, please don't, because that's actually a little bit incorrect. All right, here is another example, but in this one we do not have an explicit restricted domain. But you should be a bit careful because sometimes the functions introduce restrictions. So for example here, because you can't plug negatives into a square root, this implies that t must be bigger than or equal to 0, since you can't square root a negative. So once again, we'll just plot some points. And let's just start by inputting 0. When we input 0, the x is 0, and the y is -5. So we start down here. When we input 1, the x is 1 and the y is -4. And you're free to input values that actually square root nicely, so let's skip ahead and input the next value of t to be 4. Then x is 2 and y is -1. And just one more, let's input t equals 9. So when t is 9, x is 3 and y is 4. And our curve goes in this direction. And this time, as there is no restriction stating a last t value we should plug in, you should indicate that this curve keeps going forever and ever. Notice what this looks like. This looks like the right half of the parabola y equals x squared minus 5. Next, we have two curves that are pretty closely related, and we're going to use this as an example to distinguish between a curve and a parametric curve. So first of all, what curve is represented by the equations x equals cosine t, y equals sine t, for t's between 0 and 2 pi? Well, let's plug in some values. So t, x, y. So when t is 0, cosine of 0 is 1, and sine of 0 is 0. So right there is our starting point. The next easy point to plug into cosine and sine probably is, well, pi over 4 isn't super hard, but root 2 over 2 is a little bit tricky to graph. It's approximately 0.7, 0.7. So ish, 0.7, 0.7. You got a point about right there. So plugging in t equals pi quarters, we get x is root 2 over 2, y is root 2 over 2, both of which are approximately 0.707. Okay, when we plug in pi halves, cosine of pi halves is 0, sine of pi halves is 1. When we plug in pi, cosine of pi is -1, sine of pi is 0. When we plug in 3 pi halves, cosine of 3 pi halves is 0, and sine of 3 pi halves is -1. And we plug in 2 pi, we're back to the point 1, 0. So this parametric equation describes the unit circle. That's your starting point, and you go around it counterclockwise. So it's a circle with radius 1, traced once in a counterclockwise direction. How about this one? Cosine of 2t, sine of 2t. What is going to change? So let's plug in some values for t. All right, we input t equals 0. And notice we do have the same restriction on t. T is still between 0 and 2 pi. So when we input t equals 0, the x coordinate is still 1. The y coordinate is still 0. So we start in the same point, at the same point. Now, I'm going to leave some space and I'm going to input pi halves, and we're going to talk about why we need another value between 0 and pi halves. If you input pi halves, you get cosine of pi, which is -1, and sine of pi, which is 0. So you're at this point. And the question is did you just go directly over to that point, or did you go up and over to that point? So we're going to need a t value that is between 0 and pi halves, and the easiest value to choose is pi quarters. When we input pi quarters, cosine of 2 pi quarters is the same thing as cosine of pi halves, and that will give us 0. And then we'll have sine of pi halves, which gives us 1. Okay, so when we were at t equals 0, we were at this point. T equals pi quarters, we're at that point. By t equals pi halves, we're at this point. Versus the previous example, whereas when we were at t equals pi halves, we'd only gone around the circle 1/4 of the way. In this one, by t equals pi halves, we got around the circle halfway. Okay, now we need to plug in 3 pi quarters. So when you input 3 pi quarters, cosine of 2 times 3 pi quarters is the same thing as cosine of 6 pi quarters, or 3 pi halves, which is 0. Sine of 3 pi halves is going to give us -1. And then inputting pi, we'll have cosine of 2 pi, which is 1, sine of 2 pi, which is 0. Okay, so that was going up to just pi. And I'm pretty sure that you should all understand that if we do this again, when we plug in 5 pi quarters, we're going to end up back at this point. And we plug in 3 pi halves, we're going to end up back at this point. So what we're going to do is we're going to trace the unit circle again. So how this curve is different is this is the circle with r equal to 1, but it's traced twice in a counterclockwise direction. And the moral of the story is that there is more than one way to represent represent that curve. So we're going to distinguish between the curve, which is just the picture, the set of points, and the parametric curve, which is how those points are traced, both direction and, if more than once, how many times. So the curve, this is just the set of all points. So in this case, the curve is just the circle x squared plus y squared equals 1. A parametric curve this is when the points are traced in a particular way. And that could include both direction plus maybe a variable number of times if the pattern is repeated. All right, sketch this curve. X equals sine t and y is sine t squared, and they don't really tell us what values to choose, so let's just pick some and see what's going on here. So t, x, y. So well, if we input t equals 0, x is 0 and y is 0, so we go through the origin. If we input t equals pi halves, well, the x is 1 and the y is 1. So we've gone over to this point. If we input pi, we're back at 0, 0. So we've gone up and then back down. If we input 3 pi halves, so sine of 3 pi halves is -1, but when I square that, I get +1, so we're up to this point. And then if I input 2 pi, we've gone back down to the origin. So that could be, it isn't quite half of a circle, and I apologize that I can't draw a better picture, but here's how you can kind of think about what that curve is supposed to be. Notice how the y is sine of t squared, which is the same thing as, since sine of t is equal to x, this is the curve x squared. But notice how it's not the entire curve x squared. This is y equals x squared just between x equals -1 and +1. So we have that the x is between +1 and -1, and this is that part of the parabola. So this is this part of the y equals x squared traced an infinite number of times. And the reason it's an infinite number of times is because we were not given any domain restrictions. We didn't know that x was between 0 and 2 pi. I just chose those values to plot the curve. Here's a similar example that's sort of best thought about in how are x and y related and what curve is this, and with what restrictions. So the thing to notice here is that y is the same thing as e to the t to the power of -2. So the reason that's true is that these exponents multiply, giving you back e to the -2t. And e to the t is x, so this is the same thing as x to the -2, or 1 over x squared. But you've got to think about the restrictions. So since x is equal to e to the t, you know that x must be strictly bigger than 0, as e to the t is always bigger than 0. So of that 1 over x squared curve, we only have the right half. Now that curve goes through the point 0, 1, and as you plug in larger values for t, the y's decrease and the x's increase. And so it's traced in this direction. So in these cases, you should not have an arrow on the right side pointing up, just have arrows giving your direction. There you go. All right, now we can also be given pictures of the x and y coordinates as graphs and then be asked to determine what curve they make. So let's start with, this is just a matching question, but we can also sort of justify why we've chosen what we've chosen. So it turns out that there are actually pretty easy ways to figure out which is which just by using the starting points. So notice that in this one, when t is 0, the x is 1, and the y is 0. So we're looking for a curve that goes through the point 1, 0. It actually turns out there's only one curve that fits that bill, and that is this third one. So this one must be A. But let's also talk about why it does the rest of the stuff that it does. Okay, so here's halfway. That's t equals 1/2. Here's t equals 1/2. So what happens there is that the x's increase to 2, and the y's increase to 1 and then decrease down to 0. So see what happens there? The x's and y's increase, and there's a point at which the y's decrease, and the x's go to 2, and the y's go back to 0. And then from this half, the x's go back to 1, and the y's decrease down to what appears to be -1, and then go back up to 0. So that's the direction in which that curve is traced. Okay. All right, this next one, you see how we have a curve that starts at 0, 0. So it begins at the origin, and the only curve that fits that bill is actually this one. So even without any other reasoning, this must be B. And let's talk about what happens initially. Okay, so here is a half, and there's your quarters. Halfway through this one is here, and there's half of the halves. Okay, so by 1/4, by t equals 1/4, what have the x's done? So the x's increased to 2 and then went back down to 0, and the y's went up to 2, down to 0, and negative. Okay, so x's increased to 2, and the y started positive. So our x's are increasing and our y's are increasing. So there's the point when they're both equal to 2. That looks like it's approximately, actually not both 2, but there's, in case we're going that direction. And then the y's start decreasing. Sending us down to the point when x is 0. So x is 0, that's going to correspond to this point. And now from here to here, the x's are negative. They go to -2, while the y's increase up to +2. And then eventually the x's are going to go back to 0, so that's this part of the curve. All right, this next portion, the x's increase to 2, go down to 0. Oh, that purple part should have been included with, this is also part of the purple part because the y's went down to 0 as well. So in our next little time chunk, the x's go up to 2 and back down to 0, and the y's go negative and back up to +2. So that's this part of the curve. And from there you can see that we're going to trace the rest of it like this. Okay, next. So the next one's a little bit more tricky because our starting, we have this, they're not the starting points, but they definitely correspond to points. So in this case, when we have x is equal to 0, the y is going to be 2. So we're looking for points that, curves that go through the point 0, 2. This one appears to go through 0, 2, and so does this one, so we can immediately say which is which. Okay, let's plot some more points then. Well, And, well, here's another way you can reason through this. This y plot has all positive values. So what that means is that this curve will only have positive y's. That means that this must be C. But we can kind of look at what's going on here. Okay. So it looks like what's happening is that the x's start negative and they go through 0, and then they go to positive 2, and then back to 0 as the y traces up to 2. Okay, so the x's start negative. So that's actually where this curve is going to start. And then they increase to x being positive 2, which is actually this point out here. And they decrease to 0. Notice how in that portion your y only has a little bit to increase to 2. That's why this part is so flat. And then on the next part of the curve, the x's decrease to about negative 2. So that's this point. Then they start increasing, get to 0, and then from that point on they keep increasing while the y values get closer and closer to 2. And then by process of elimination this must be D, but that's not the greatest way to take it. So let's also discuss what's going on here. Okay, so our starting point seems to be the point 2 for x, negative 2 for y. So over 2 for x, negative 2 for y seems to be about right there. And then you see how this point kind of corresponds to that much distance on that axis. So what's going to happen is your x's decrease and your y's kind of stay the same. So x decreasing means x is going negative, so x heads off to the left, and the y's stay the same. Then from there on, the x's increase and the y's increase until they're at the point which appears to be x is 2, y is 2, approximately. So that's this part of the curve. And that's the point where we've got 2, 2. And from that point, the x's appear to remain mostly constant while the y's decrease. So the x's remain constant means a vertical line while the y's decrease. And it gives you that kind of triangle shape. So in some earlier examples, we were able to sort of figure out what the curve was related to by writing it as a regular Cartesian curve by sort of getting rid of the parameter using the relationship. That's called eliminating the parameter, and how you figure this out is you can try to say solve this equation for t and then plug it back in. So here you can solve either one for t. I'm just going to choose to solve x for t. So x plus 5 equals 3t, and t will equal 1/3 times x plus 5. And that can get input for y. Y is input for t in y's equation. So y is 2 times 1/3 times x plus 5 plus 1, or 2/3 times x plus 5 plus 1, which is 2/3 x plus 10/3 plus 1, or getting the common denominator, 2/3 x plus 13/3. So this set of parametric equations represents a line. And there appear to be no restrictions given, neither implied nor explicitly. All right, here, well, we can do this many ways. I think it's possibly, and I can show you both. I think, first of all, my impression is, well, we could just say that x squared equals t, and therefore y would equal 1 minus x squared. The thing you have to be a little bit careful there is that because x is root t, this implies that t has to be bigger than or equal to 0, which means that the restriction here is that x will be bigger than or equal to 0 only. Another way you could do this is you could solve the other equation for t. So y minus 1 equals negative t. T would equal 1 minus y. And so x would equal the square root of 1 minus y. And the fact that that's a square root will actually already have the restriction built in. So both of those are correct. And you could solve this expression for y and show yourself that it's the same thing. X squared equals 1 minus y. X squared minus 1 equals negative y, and y would equal 1 minus x squared. So it's the same thing. Just watch out for restrictions that are implied because you have restrictions on your parameter t. You may also be given restrictions explicitly, and I think in that case it's actually best to kind of graph the curve and look and see what the restrictions are on either the x or the y. Now you have two options here. You can either solve x for t, that's going to involve a square root, or you can solve y for t, which will not involve a square root. I think it's better to solve y for t. So y minus 5 will equal negative 2t, and negative 1/2 times the quantity y minus 5 equals t, and x will equal negative 1/2 y minus 5, that whole thing squared, minus 2, or 1/4 times y minus 5 squared minus 2. And so that's sort of good enough. Okay, now this is going to be a sideways parabola with vertex at -2, +5. And I just know what's going to happen here, so I'm going to actually make my axes count by 2s, both of them. So back 2, up 1, 2, 3, 4, 5. And now the question is what's going to happen at my endpoint. So at t equals -3, the x equals 9 minus 2, or 7, and the y will equal 5 plus 6, or 11. So over 7, up 11. So 2, 4, 6, 7, 2, 4, 6, 8, 10. There's our starting point. And you're going to go in this direction towards that point. One reason you can tell that is that this y has negative slope, so the y's are going to decrease. And at t equals 4, your x-coordinate will be 16 minus 2, or 14. And the y-coordinate will be 5 minus 8, or -3. So there we are. So the curve is traced in that direction. And so I think it probably is best, you could give restrictions on the x's, but really this is a function of y, so you're going to give restrictions on the y's. So the lowest y value you plug in is -3, and the highest y value you plug in is 11. All right, y equals sine t and y equals cosecant t. Now, probably not wise to use arcsine and stuff with these. There probably is an easier relationship, kind of like the example that we had where y was sine squared t and x was sine t. In that case, that was a really easy relationship that we just replaced the sine t and y with x. And so in this question that we have, we've got x equals sine t, and well, cosecant t actually is sine t in disguise. It's 1 over sine t. And so therefore y is 1 over x. So there is the Cartesian equation. Now, there are restrictions. So these restrictions are t must between 0 and pi halves, non-inclusive of those endpoints. So we can't actually plug in 0, but t equals 0 does imply that x equals 0. So that probably is the left end. That's the left endpoint of our interval. And if t equals pi halves, well, then x would equal 1. So it looks like we're restricted to the interval from 0 to 1. And here's what this would look like. 1 over x is this reciprocal function that goes through the point 1, 1. And it usually has this half, and it has this half. But because we have this restricted domain from 0 to 1, the only part that we include is this bit. And there actually has to be an open circle there, because you cannot actually, in this case, because of the strictly less than pi halves, you can't plug in 1. And the other question is, what is the direction of this curve? Well, from 0 to pi halves, think about what happens to the sine coordinate, which is the x-coordinate. The sine coordinate begins at 0 and goes to 1. So sine begins, the x-coordinate begins at 0, goes to 1. That means you're tracing this curve down. And the y-coordinate is 1 divided by that number, and that x is approaching, so it's approaching the point when you have 1 over 1. I guess we already did this, but let's do it nicely. So we have an open circle at the point 1, 1, and the curve is traced in this downwards direction. All right, let's sketch the curve represented by x equals 5 sine theta and y equals 2 cosine theta on the interval from 0 to 3 pi halves, and then we're also going to eliminate the parameter here. Okay, so let's make a table of values. We have theta instead of t, but that's no big deal. X and y. All right, so when theta is 0, sine of theta is 0, and cosine of theta is, cosine of 0 is 1, multiplied by 2 gives us 2. So we're at the point x is 0, y is 2. I'm going to subdivide the interval and call that the point 0, 2. The next easy number to plug in would be pi halves. When x is pi halves, sine of pi halves is 1, so my x is 5. And cosine of pi halves is 0, so that's 0. So 1, 2, 3, 4, extend, make it 5. So we've gone over to this portion. Okay, then plugging in pi, sine of pi is 0, cosine of pi is -1, multiplied by 2 gives us -2. So back down to here. And plugging in 3 pi halves, the x will be -5 and the y will be 0. All right, so there is the parametric curve. This looks like an ellipse, like a squashed circle. Now, in this case, it is better to not, you definitely shouldn't use arcsine and shouldn't use arccosine because you're going to have to do some tricky trig to simplify those expressions. So here's how we're going to do this instead. We know that x over 5 is sine theta, and y over 2 is cosine of theta. And then use your favorite trigonometric identity that says that cosine squared theta plus sine squared theta must equal 1. And input the things that you know. You know cosine of theta is y over 2. So y over 2, the quantity squared, plus x over 5, the quantity squared, equals 1. And so that's y squared over 4 plus x squared over 25 equals 1. That's the Cartesian equation for this ellipse. I'm not going to worry too much about domain restrictions here because it's a bit tricky to do this right. You could say it's sort of 3/4 of this ellipse, but the picture describes how much of it that you have, so that's totally enough. Now, there are lots of ways to find parameterizations for equations, and we're not going to do a whole lot of this, but it's just good to have an idea of how you can do it. So the simplest way is to, if you're given an equation like y equals 1 plus x squared and you want to parameterize it, you could just say, okay, well, I'll let x equals t, and in that case, my y would equal 1 plus t squared. And technically, that is a parameterization. It's a bit of a silly, simple one, but it is. You have x as a function of t and y as a function of t, and if you graph this for various values of t, you're going to get a parabola traced in a specific direction. Another way we could do this is we could parameterize using the slope of the tangent line at a given point. So notice that y prime is equal to 2x. So my parameterization could be m equals 2x, which would imply that x is slope divided by 2. And then my y would be 1 plus that m over 2 squared, or y would equal 1 plus m squared over 4. And that set of equations, x equals m over 2, y equals 1 plus m squared over 4, will also give me the graph of 1 plus x squared. It's just going to be traced at a little different rate than the other one. Kind of like those two circles were both traced and then shift both traced, but one was traced one more time than the other. All right, now what would a parametric equation for a circle with center h, k, and radius r be? And kind of use stuff we've done in this lesson to figure this out. We know that if we let x equals cosine t, y equals sine t, this traces a circle with r equal to 1. So if we want to trace a circle with radius r, where r might not be 1, what we could do instead is let x equal r cosine t, y equal r sine t. And this will do a circle with radius r and center 0, 0. Now then the question is how do you get that circle over to your center, which is over h up k? And so the thing is you have to plus h to the x-coordinate and plus k to the y-coordinate. If that k or h happen to be negative, you'll be adding a negative, which would then move that circle down. So the x-coordinate will be r cosine of t plus h, and the y-coordinate will be r sine of t, and we have to plus k in that case. Now, another way to convince ourselves that this is correct is to somehow eliminate the parameter and show that this gives us x minus h squared plus y minus k squared equals r squared. And here's how we're going to do that. This first equation, we have x minus h equals r cosine of t. And we also have that y minus k is equal to r sine t. And so then x minus h squared plus y minus k squared is going to equal r cosine of t, the quantity squared, plus r sine t, the quantity squared. And that has to be true because if this equals that, those two things must be equal. And if y minus k equals r sine t, these two things must be equal. So if I take this equal this thing and that thing, and add this thing and that thing on the other side, we're just adding two different sort of expressions that are the exact same value. So it doesn't really help to simplify the left side because we already have it sort of in the form we need it. But the right side, well, that's r squared cosine squared t plus r squared sine squared t, which is r squared times cosine squared t plus sine squared t. And cosine squared t plus sine squared t is equal to 1. So we get that this is equal to r squared. And so that sort of shows that the parameterization that we thought would parameterize a circle of radius r centered at hk did actually indeed do what we needed it to do.